Okay, so in this video, what we're going to do is prove the Mostowski collapsing theorem. And so what does this theorem say? This is the Mostowski collapse. Mostowski collapse. And so what does it say? It says, well, if we have a well ordering, so if a comma less than is a well ordering, well, then there's a unique map pi and a unique ordinal alpha, so that pi is an order isomorphism from A into alpha. Then there exists a unique pi and a unique ordinal alpha, so that such that pi is an order isomorphism. And we mentioned this last time, but this thing is called the Mostowski collapse. So this map pi, this is called the Mostowski collapse. Okay, so how does the proof of this thing go? Well, it's going to break up into a few different stages. Because on one hand, what we need to prove is that there is such an order isomorphism, and then we want to show that everything's actually unique. Okay, so how does the proof of this thing start? Well, I need to tell you what this map is. And well, we talked a bit about where this kind of intuition for this definition of pi came from in the previous video. So I checked that out if this is a little bit kind of coming out of nowhere. But what we're going to do is we're going to define this map pi by induction. So by recursion, I guess. So by recursion, well, A is a well ordering, so we can do recursion on A. So what we're going to do is define pi of A to be what? Well, we define it as the set of all pi of B such that pi is less than A. So in other words, what happens? In recursion, you assume that you've defined all the previous, so you're at a value A. So I guess we'll mention here that, well, A is an element of our big well ordering of our well ordering A. And well, what are we doing? We're assuming that we've defined this map pi for everything less than A. Well, if we've defined pi of B for all B less than A, there's nothing stopping us from taking the set of all of those things. Why is it a set? Well, there's only the kind of collection of elements that are less than A. Well, that's a subset of our well ordering, and so it's also going to be a set. Okay. So we can define this. This is going to be our mapping pi, and well, what is going to be the kind of the ordinal? Well, it's going to be the pointwise image of all of these kind of mappings. So in other words, so maybe I'll write it out like this. So let's define further. Well, after we've done this whole recursion, there's nothing stopping us from defining alpha. So define alpha to be the pointwise image of A. And now this is notation that tends to be more common for set theorists. But when I use this pi with the quotation marks, what I mean is the set of all pi of A such that A is in big A. And there, so I guess if you've taken discrete math or other classes like this, maybe you've seen kind of these closed brackets to represent the pointwise image of something. But in set theory, it's a little bit more common to use these quotation marks. And when we start doing more advanced kind of set theory, we'll hopefully see why. But one reason for why it might be an issue is that actually even with ordinals, right? So let's say that we have a function that's defined, and again, this is a little bit of an aside just to justify this notation for a second. Let's say that we had some kind of function, I'm putting in air quotes because there's no set of all ordinals, but let's say that we had a function defined on all the ordinals, and it's into like, I don't know, some other kind of set, or maybe it's a proper class. Well, if you have an ordinal, you could consider two different things, right? On one hand, you could think of f of that ordinal, right? You could say, well, if we view this as a mapping, what is alpha getting sent to? But what is an ordinal? It's a set of ordinals. And so you could also ask the question, what is the pointwise image of alpha, right? If we view alpha as a set of ordinals. And so in that situation, it would be extremely confusing to use or maybe there's a potential for extreme confusion to use these closed brackets to represent the set of all kind of outputs. So we don't want to use this as the pointwise image because this can be very easily confused with just the image of alpha under F. And so what we use instead for this is the quotation marks, just to kind of really make it clear that we're not talking about the image under F of our kind of ordinal alpha, but we're thinking about alpha as a set of stuff, and we're looking at the output of all the stuff inside of alpha. Okay, a little bit of a digression, but again, kind of saying why we kind of tend to use these quotation marks. Okay. All right, so we defined alpha to be this to be this set here, the pointwise image of A. And so what we want to do now is we want to check that pi. So we need to our goal now is to show, well, pi from A into alpha, this is an order isomorphism. And I guess one more thing, maybe we don't. We will also want to check that alpha is an ordinal, right? We defined alpha as the pointwise image of this thing, but we could use Greek letters to represent any type of set that we want. We should hope that it's actually an ordinal. And the alpha is actually an ordinal. This would be nice. Well, one thing that we can do maybe to kind of start kind of towards that goal is check that. Well, what is an ordinal? An ordinal is a transitive set that's well ordered by epsilon. So maybe we can first check that alpha is transitive. So maybe here's a claim that alpha is transitive. Now, why is this true? So what's the proof? We'll call this claim 1. Claim 1. So what's the proof of this claim 1? Well, how do we argue that something's transitive? We need to take an element and show that it's a subset of it. So that's one way to do it. But another way to do it is to kind of use this kind of equivalent statement of what it means to be transitive. So assume, do we want to do it like that? Maybe it's better to kind of do it the way I said it originally. So let's assume that we have some x that's an element of alpha. But what is alpha? Alpha is equal to the pointwise image of A. So what has to be the case then? Well, then there's some A. So there's some, say, A in little a in our set big A, such that, well, x is equal to the image of A under pi. So such that x is equal to the image of A under pi. Okay. Now, what's our goal now? Our goal is to show that, well, alpha x or pi of A is actually a subset of the pointwise image of A. So what's our kind of goal now? Our goal now is to show that, well, x is a subset. Maybe since x is equal to pi of A, we'll be a little bit more precise. So pi of A, we want to show is a subset of alpha. So how do we do this? So we can say, we'll fix some y that's an element of pi of A. And so what do we know by definition? Well, pi of A is equal to what? This is equal to the set of all pi of B, such that B is less than A. So what has to be the case is that there's some B less than A such that y is equal to pi of B. So there exists some B less than A such that pi of B is equal to y. But maybe I'll write it like this, such that y is equal to pi of B. So y is equal to pi of B. But, well, by definition of alpha, this thing's an element of the direct image of pi, of A under pi. Right? That's just what, by definition, pi of B is going to be inside the direct image of pi under A. But that's what we wanted to show, right? Because this thing is equal to alpha. Right? So what did we just show? If we took some element y in pi of A, it's actually also an element of alpha. But then that's what it means for alpha to be transitive. So we're done in this case. Okay. All right. So we checked that it's transitive. Now what we want to do, I guess, to check that it's an ordinal is to show that it's well ordered by epsilon. We can also check that it's a transitive set of transitive sets. That's maybe an easier way to do it. But we can maybe do it more directly by showing actually that this is in fact an order isomorphism. Well, how would this work? Well, if we show that this mapping pi is an order isomorphism, well then it's since A is a well ordering, well its image under pi is also going to be well ordering, but its image is going to be alpha. So what is alpha then? It's a transitive set that's well ordered by epsilon, and so then it's actually an ordinal. Okay. So what's our goal now? Our goal is to check that that pi is in fact an order isomorphism. And one kind of mini step towards doing this is actually maybe we'll kind of first say that to be an order isomorphism you need to be a bijection. Well, that includes being 1-to-1 and onto, but we don't actually need to check onto-ness because, well, just by definition of alpha, it's kind of trivially onto. So what's so I'm gonna say just fact. I'll list this as a fact that pi, when viewed as a map from from A into alpha, this thing is onto. Right, just by definition of alpha. So by definition. So by definition of alpha. And so what we need to check now is just that, well, pi is 1-to-1, which we'll do first. Then we want to actually check it's an order isomorphism. And then finally what we want to check is that it's unique. Okay, so what's our claim 2? That's going to be, let's check now that it's actually 1-to-1. So claim 2. And so pi is 1-to-1. And well, what does this mean? This means, again, just that, well, if you take any two elements of A, well, if their images are equal, then they're actually equal. So this is what we want to check. Right, you can also express this as it's contrapositive, right? If you have two distinct things, they map to distinct things. But for us, it'll be a little bit easier to work with this. And how can we prove this? Well, we can actually prove this by induction. So what's the proof of this? Proof of 2. What we're going to do is we're going to do induction on A. And we have to be a little bit clever, right? What are we doing induction on? So what we're going to say is, well, let P of A be the statement, well, for all B, if pi of A is equal to pi of B, well, then A is equal to B. And so in order to show claim 2, it's enough to show for all A, P of A. So it's enough to show. So it's enough to show for all A, P of A. And so what we're going to do is we're going to prove this statement by induction. So we're going to proceed by induction. Proceed by induction. And so how does the induction work? Well, we're going to assume that it's true for all, say, C less than A. So assume for all C less than A that P of C holds. And what does this mean? And I think it's good to write out what this means. This would mean something like, well, for all C less than A, well, then for all B, if it's the case that pi of C is equal to pi of B, well, then it's the case that C is equal to B. Right? That's, I kind of added an extra bit of close brackets, but that's what this statement means. And this is what we're assuming is true. And the crucial thing here is that, well, this second quantifier does not depend on A at all, right? This could be any value of big A, our well-ordered set. And, well, where this one is all the values that are less than A. So that's going to be pretty important for us. Okay, so how are we going to work through this? We could say something like, assume that we have some B. So our goal is to, so what's our goal? Our goal now is that we want to show that P of A holds. Right, that's what we'd want to check in our induction. And well, how can we do this? Well, fix a B such that pi of A is equal to pi of B. So fix any B, so any B in our big A such that pi of A is equal to pi of B. And our goal, of course, is to show that A is equal to B. And what we're going to do, and I'll let you kind of think about this as an exercise, is, so I'm going to say that it's enough to show the following. Well, if you have any element in our set A, so it's enough to show I'll write it out. So it's enough to show. So it's enough to show that, well, for every single element, I guess, of our well-ordered set A, well, it's enough to show that it's less than A if and only if it's less than B. And I encourage you to kind of maybe think through why exactly this works. But, well, if this is the case, I mean, we can think about it like ordinals, right? This would be true for ordinals, right? Because the epsilon relation on the ordinals, or the less than relation, is the epsilon relation. And we've proven that, well, being less than or equal to as an ordinal is the same thing as being a subset. Okay, we don't really, I guess, we can't appeal to that. That's a little bit circular because we don't know that A is isomorphic to an ordinal yet. But, you know, if we have well orderings and we have two elements that agree on the set of predecessors, they're actually, you can prove that they're the same element. So I encourage you to kind of leave it as an exercise. So exercise that this implies that we're done. So exercise that this is enough. And again, it's without appealing to the fact that it's true for ordinals. We'd want to kind of prove it just directly using, I guess, that well orderings, you know, non-empty subsets have least elements, stuff like that. Okay, so how do we do this? Well, we can just pick one direction. So assume, you know, kind of mark it here. Assume that C is less than A. And, well, what can we say from this? We don't know that pi is an order isomorphism, but what we can say by just the definition of pi of A is that if this is true, so then, by definition of pi, so by definition of pi, it must be the case that pi of C is an element of pi of A, right? Because pi of A is the set of all pi of B such that B is less than A, but C is less than A, so it's going to be an element of the set. And what are we assuming now? We are assuming that pi of A is equal to pi of B. So this thing is equal to pi of B. And so now we can unravel this definition for pi of B. Since pi of C now is an element of pi of B, there has to be some, say, C prime that's going to be less than B, right? Importantly, I guess that by definition, pi of B is the set of all, you know, pi of X such that X is less than B. There has to be some C prime less than B such that pi of C is equal to pi of C prime. Okay, but now what we can do is appeal to the induction hypothesis. C, by assumption, is less than A. And so that means that, like, the one-to-oneness of pi holds for C. So in other words, we have that pi of C is equal to pi of C prime. By this claim, so by kind of this claim over here, what has to be the case is that C is equal to C prime. So this is going to be by induction. Well, if this is true by induction, well, what do we know about C prime? C prime is less than B, right? By definition of where C prime came from. But that's what we wanted to check in this direction. We assume that we had an element that's less than A, and we just argue that it's less than B. So that's kind of good in this direction. Well, I'll kind of also leave it as an exercise, but going backwards is the same type of an argument. So checking that if, actually, maybe we'll just write it out. It's not that much more work. So if C is less than B, what we can say, we can do the same thing. Well, this implies what? This implies that pi of C is an element of pi of B by definition of pi of B. Well, this implies what? Well, this thing is equal to pi of A. And so that means that there's some C that's say prime, say that's less than A, such that pi of C is equal to pi of C prime. And so now what we can say, we have to be a little bit careful, but now we can imply the induction hypothesis to C prime, right? We've assumed that, well, pi is 1-to-1 for all values less than A. Well, C prime is less than A. And so that means that we can imply the induction hypothesis to C prime. And so what we have to conclude from this is that C is equal to C prime. Maybe we'll kind of mention, since pi of C prime is true. And again, importantly, it's that because pi of C prime is true, we could quantify the second term as we can quantify this the second term is quantifying over all values of a, not just all the values less than our little a right there. Okay. And so then what we can say is that c is equal to c prime, which is less than a, which is what we wanted to check. If we have something that's less than b, it's also less than a. Okay, but then this finishes our claim by our exercise, right? We've checked that two elements have the same set of predecessors, and because a is a well-ordered set, it must be that they're actually the same. Let's see. So a is equal to b. And then, well, this checks then that, well, the induction hypothesis goes through, so p of a holds. Well, that means that, well, pi is actually 1 to 1, which is what we wanted to check. So we just checked that pi is 1 to 1. Okay, what's the next thing that we want to do? The next thing that we want to check is, well, pi is actually an order isomorphism. So pi is an order isomorphism. Maybe I'll just write out what this means. Well, this would mean something like for all a and for all b, it's the case that a is less than b if and only if pi of a is an element of pi of b. We're reviewing the right-hand set. Its ordering is the epsilon ordering. And so how do we do this? This right-hand direction is something that we kind of already used, and it follows just from the definition of pi. So this direction, so what's the proof of this? So this direction follows by definition of pi. Well, this in the backwards direction, we're actually going to use the fact that pi we just proved is 1 to 1. So how does this backward direction go? So assume let's assume that pi of a is an element of pi of b. And well, what does this mean? Well, by definition, it means that there's some, say, a prime less than b, such that pi of a is equal to pi of a prime. So this implies there's some a prime less than b, so that pi of a is equal to pi of a prime. But we know, we just proved that pi is 1 to 1. And so that means that a is equal to a prime, but a prime is less than b. So then, maybe we'll say since pi is 1 to 1, well, this implies then that a is equal to a prime, which is less than b, which is what we wanted to prove. Right, that's our end of 3, right? Because we just showed that if pi of a is an element of pi of b, then a is actually less than b, which is what we wanted to show. Okay, but this is actually everything to check that, what did we just prove? We just proved a few different things. First off, that pi is a bijection. Why? Well, it's onto trivially, right, just by definition of alpha. Well, it's 1 to 1, that was our claim 2. And we also just checked that it's an order isomorphism. That's this third claim right here. So what just happened? Well, so maybe I'll mention the previous claims show that, well, this map, this is an order isomorphism. So we've done that. And then why is alpha an ordinal? Well, this mapping we just proved is an order isomorphism. Alpha is transitive. That was the very first claim. The very first thing we checked over here was that alpha is transitive. And well, alpha is transitive. This mapping is an order isomorphism, and so the pointwise image of A will be a well ordering. So further, or maybe I'll say this implies that the pointwise image of A is a well ordering, or is well ordered. So which is alpha, right? This is alpha by definition, is well ordered. Well, by what relation? By epsilon. So by epsilon. By epsilon. Okay, but then alpha is a transitive set, well ordered by epsilon, so alpha is actually an ordinal. So alpha is an ordinal. So it's actually an ordinal. It is actually an ordinal. Okay, and I'll kind of mark this as the end of the existence, right? We just checked that, well, there is a map called the Mostowski Collapse. That is an order isomorphism. The range of this order isomorphism is an ordinal. And now what we want to do is check that this mapping is actually unique. And what we're going to use is one of our kind of technical lemmas that we proved in the last video, that if we have some order isomorphism between two ordinals, then it's actually that order isomorphism is actually the identity map, and the ordinals are actually equal to each other. So let's write it out. So to show uniqueness, what we can do is assume, maybe we'll call it pi 0. This is maybe a map from A into alpha 0. This is the first, maybe some witness of this previous result. And we also have maybe the same set A into alpha 1. So assume that these are order isomorphisms. So order isomorphisms where alpha 0 and alpha 1 are both ordinals. And the trick is to, well, compose these things in the right way. And I'll kind of leave some details for you to check that if you take, say, the inverse of an order isomorphism, you also get an order isomorphism. And also that if you compose order isomorphisms together, you also get an order isomorphism. So maybe I'll just say, well, if you look at pi 0 inverse, so that's going to be an order isomorphism from alpha 0 into A. So if we did pi 1 composed with pi 0 inverse, what is this going to be? Well, pi 0 inverse is going to start with alpha 0. We're going to go into A. But then pi 1 goes from A into alpha 1. This is going to be an order isomorphism from alpha 0 into alpha 1. So it is an order isomorphism. Well, what did we prove last time? We proved that, well, then alpha 0 is equal to alpha 1. So from last time, maybe I'll call it alpha now. So alpha is equal to alpha 0 is equal to alpha 1. So these two ordinals are the same, so we'll just call them alpha. And further, that pi 1 composed with pi 0 inverse is the identity map. And so this second claim actually implies that pi 0 is equal to pi 1, which is what we'd want to do. So this implies pi 1 is equal to pi 0, which is what we want to check, right? If we had kind of a mapping pi 0 from A into alpha 0 and a mapping from pi 1 from A into alpha 1, we want to check not only that alpha 0 is equal to alpha 1, but that pi 0 is equal to pi 1. And that's what we just argued. Maybe to kind of say a little bit more about how we kind of go from here to here, what we could check is, maybe we'll do it like some intermediate step. But what we want to check is that we want to show that pi 1 is equal to pi 0. So that means if we take any element of A, pi 1 of A is equal to pi 0 of A. One way to do this is, well, if we take some element A, well, pi 0 of A, this thing is an ordinal. And in particular, it's going to be less than alpha. Right, it's going to be less than alpha 0, but we just checked that alpha 0, or from the previous result, alpha 0, or from one of the results from the previous video, alpha 0 is just equal to alpha 1, which is in our case alpha. Okay, well, what do we know about this map here? Well, this pi 1 composed with pi 0 inverse, this is a function from alpha 0, so alpha into alpha. Well, there's nothing stopping us then from saying, well, then, if we view this as our kind of element on the right-hand side, pi 0 of A, that's going to be equal to what? Well, that's going to be equal to pi 1 of pi 0 inverse of pi 0 of A. I'm flipping the order. I'm using the identity map on this left-hand side. So our B is, if we want to say, like, B is equal to pi 1 of pi 0 inverse of B. Well, our B in this case is pi 0 of A. And now what we can just do is cancel out these inside terms. The pi 0 and the pi 0 inverse cancel, and what we're left with is pi 1 of A. Okay, so this then checks uniqueness. But then we're done. We just not only checked that we have an order isomorphism from a well ordering into an ordinal, we checked that we checked then that the order the ordinal is unique, and also the order isomorphism is unique, which justifies, I guess, the name. Well, now we can call this the Mostowski collapse, right? There's only one of them. Okay, so yeah, so we'll kind of call it a day there. I'll see everyone in the next video.